14.3b2 The resonance tube experiment to determine the wavelength of sound using stationary waves. Question 1. Describe the method. Question 2. The end correction. Sub-question 1. What is the end correction? Sub-question 2. How to eliminate errors brought by the end correction. Question 3. How the idea that the representation of standing sound waves can be misleading. So, what's the method? As shown in this figure, a glass tube, open at both ends. One end dips into the water contained by this cylinder, and the other end is in the air. A vibrating tuning fork is placed at the end of the tube, so the air in the tube will be forced to vibrate to produce sound waves, which will be reflected back from the surface of the water. So a standing sound wave can be produced in this part of the tube. If this happens, and you put your ear at the end of the tube here, the sound you hear is much louder. In order for this to happen, the length of the air column must be appropriate. Let's see another figure. This is the air column in the tube, and the green lines in it represent the standing wave. As we can see, at the bottom of the air column, here must be a load. That's because the air here cannot vibrate up and down. It was stopped by the water below. However, the air at the top of the air column, at the open end of the tube, can vibrate up and down most freely. So here must be the position of an antinode. And that's also the reason why the sound heard here is much louder. Accurately, it's 2/10 of the normal loudness. Now back to the length of the air column. So now you know what's the appropriate length of the air column for a standing wave to occur in it. The smallest length is 1/4 of a wavelength, and the second smallest length is 3/4 of a wavelength, and so on. So if we measure these lengths, we can calculate the wavelength. And then, if we know the frequency of the tuning fork or the sound wave, we can calculate the speed of sound wave in air. And this is the basic method and principle of this experiment. In addition, there is something not shown in this figure. This tube is clamped by a clamp which is fixed on a retort stand. So it's easy to adjust the height of the tube to change the length of the air column. Then how to determine when there is a standing wave happening? We are not using our ears to hear, but putting a microphone or headphone here to detect the amplitude of the sound wave, which can be shown on your smartphone if the headphone is connected to your smartphone and an appropriate application is installed in your smartphone. So the apparatus of this experiment is simple and easily available. You can conduct this experiment even at home. And now let's move on to the second question, which is about the end correction. So what's the end correction? If we look closely at the figure, we'll see the antinode is slightly beyond the top end of the tube by a distance of c. This is because experiment shows that the air slightly beyond the end of the tube vibrates as part of the standing wave, and the distance c is what we call the end correction. Now I'll ask you, if you calculate the wavelength from the length of the air column without accounting for the end correction, how is your result? Is it smaller or greater than the true value? Or is it exact same as the true value? Yes, the value of the wavelength you get is smaller than its true value. So how to reduce this error? The bad news is we do not know the value of c. It cannot be measured directly, but we can do some mathematical tricks to eliminate the error brought by the end correction c. For this shorter tube, we can write a quarter of a wavelength equals to L sub 1 plus c. L sub 1 is the length of the air column. And for the longer tube, we can write 3/4 of a wavelength equals to L sub 2 plus c. L sub 2 is the length of the air column here. And then subtracting the first equation from the second question gives this equation. Simplify it, we get 1/2 of a wavelength equals to L sub 2 minus L sub 1. So the end correction c is cancelled out. So here we get lambda equals to 2 times L sub 2 minus L sub 1 is the value without the error brought by the end correction. And so this is what we should know about the end correction. And the last thing you should know is the representation of standing sound waves in this video or textbook or any other books can be misleading. Remember that a sound wave is a longitudinal wave, but the diagram we draw is more like a transverse wave, and this is how we normally represent a standing sound wave. It looks like a transverse wave, and the particles in which the particles vibrate left and right. But actually, the particles in the air are vibrating up and down.